So, welcome back to class. Let's see. Where we left off was talking about strong acid, strong base calculations for titration. Titration is the in-lab analytical method for neutralizing an acid and a base. If you're a strong acid, that means you completely ionize. Like for every H positive you can lose, you do. For a strong base, you completely ionize your OH minuses if you have them, or you're just really good at accepting. Like both are really good indicators. Either way, by Bronsted-Lowry definition, you just accept every single possible H plus you could. And if you have an OH minus hydroxide group, that is a good indicator that you're going to do that. You're structurally set up to accept. Okay. The calculations that we went through were pretty straightforward in terms of the individual parts, right? But we dealt with a particular problem of excess ion. With strong acid, strong base, neutralization always occurs when your moles of acid stoichiometrically equal your moles of base. And for a strong acid, strong base, that's when pH equals 7. Because oftentimes a strong acid, strong base is monoprotic. Often, not always. Okay. But it ends up being, for the most part, really straightforward at the neutral point. That is when you reach your completed reaction. You don't have any excess. But sometimes we do get excess. And so the question was, what happens when we have excess strong base or acid left over past neutralization? And we did a really basic mathematic process, but what we really cared about is then what would the resulting pH or pOH be, depending on what perspective you look at, but we tend to prioritize pH. All right. And we did some math problems where you had to, of course, initially account for dilution. That's a big thing with any titration problem, any acid base titration problem, okay, is you want to account for dilution first, okay? So, then what you do is, given the new diluted molarities, you make sure that your molarity of acid or base are equivalent to the acid or base ion produced. And then you go in and you determine what's the excess. And then from there, based off the excess ion present, you determine the pOH or pH. You might have to work backwards from pOH to get to pH using the equation Kw equals concentration of acid times concentration of base, or 14 equals pH plus pOH. All right. So that's kind of what we did. And I showed you two problems that involved using both of those equations. Okay. And so for this one down below, you should have gotten for the diluted, okay, amount. Do we have any problems with dilution calculations? Are there any problems with that? Do we feel okay with those? So for the acid, you should have gotten, based off of this problem, that the dilution is 0.1333 molarity. The reason that you probably got, if you got a smaller number than this, half of this, it's because you forgot to account for 2 protons being present in the polyprotic. So you'd have to multiply by 2. Okay, there's an 2 ion complex of 2 protons being lost, so it doubles your acid concentration. Yes, polyprotic, polyproton. So it can become SO4 2 minus. So just keep that in mind, that this H2SO4 is polyprotic. So you can lose 2 ions for every 1 H2SO4, you get 2 H pluses. Okay. So next thing, you got OH minus. Okay. 0.4 times the diluted measurement, you should have gotten 0.2667 molarity. Okay. And then what you would have seen is that right now you definitely have excess, okay, excess hydronium, or sorry, not hydronium, hydroxide, so base. So you would have gotten that the excess base, that not extra small, but excess, is 0.2667 minus 0.1333. And that gives you 1.3 or 0.1333 molarity of excess. And then what you would have done is, I would have just used the pH equals pOH. You could have also used KW. Either one would have been fine. 14 minus pOH, and you could easily find pOH from taking the negative log of 0.133. You could have also done KW. But the problem is you'd have to go through kind of like a whole cycle to find what the concentration of the acid is in terms of the water autoionization. So this ends up being quicker. Okay. And you would have gotten that a pH of 13.125 to 366.
How do we go from molarity to the pH?
Negative log of your molarity.
Negative log of the excess or that, right?
Yeah, the excess. Mm-hmm. That's XS. Excess. Looks like extra small or apparently X3, but that's an S. Okay, I'm watching Keaton judge me. I'll fix it. No, it's okay. I was just watching me squint, so I was like, okay, I'll fix it. If Keaton can't even read it, and Keaton's using my handwriting.
All acids. Do all acids that have like multiple hydrogen atoms, do we have to multiply the molarity by the amount of hydrogen atoms in the molecule?
Yes, because you want to know how many acids. You want the acid's molarity in terms of the acid's ions. So if you're trying to get to if you're trying to understand the moles of neutralized H plus, you need to understand how many moles of H plus you're getting when it dissociates into water.
So any acid molecule that has more like it can release all of its hydrogen atoms.
If it's a strong acid, yes, it loses all of its hydrogen. All right. So for the next problem, okay. This one, you had to work backwards. You were given the pH. So from pH, you can find the concentration of H plus by doing 10 to the negative pH. And that would have given you 0.010 molarity. Okay. And then you would have found that the POH, because you want to find what POH is as well. Okay. You would have had to find that the POH is 14 minus the pH that you found. And that would have given you 2. And then from there, you could find the concentration of the OH. Okay. So this was a workaround way. And you would have found that the concentration of OH is also 0.010 molarity. Okay. And then what you say is, okay, diluted wise, we need to figure out what it is diluted. So what we see here is that we go 35 plus 15, so it becomes 50. So when you do your dilution calculations, you would be multiplying by a factor of original milliliters over 50 milliliters to get your dilution, right? And you would find that your diluted value for H plus is equal to 0.0070. And your diluted value for OH minus is equal to 0.0030. Okay. And so then what you would find is obviously we have excess acid. So you would see that here our excess is equal to 0.0040 molarity. And then what you would were asked was to find the pH of the final solution after being mixed. So you would just plug this into pH. Negative log of this, and that gives you 2.40 to the correct sig fix. That's what we've been getting this whole time. That's so true. Yes. So POH, is it 12? From the POH scale, it would be low numbers because now you're looking at from you're a better base. So your pH value would be, you're thinking that it should also be a high number, right? Because it's a base. But from the pOH scale, you're better based on the base scale. So you're lower.
So, but if it's 14 minus pH, isn't it pH 2? Well, it's gonna be-
Oh, maybe I am just the idiot. Oh, yeah. No. No, because it's 12 for pH. So 14 minus pH is 12, according to the problem, minus 12. So then it's 2.
Oh, okay.
Okay. All right. So that's strong acid, strong base calculations. We're gonna move now into weak acid, weak base. Okay, weak acid, weak base. So, acid ionization constant, Ka. We've already talked about this in unit 7. So this is unit 7 specific to acid base. Okay, so what we have here is the general equation for an acid, a weak acid, is HA, some protonated acid, plus water. So here we're showing a hydrolysis reaction. We're just isolating it to reaction with water. Because right now we're just trying to characterize the acid. So of course we don't want to do a true neutralization. And it is in equilibrium. And it forms H3O plus and A minus. So our Ka equation then becomes, our setup was products over reactants. So products is the H plus times the concentration of the conjugate base divided by the original acid. Right? And so for the weak base, we have a similar setup, just analogous to the base. So it becomes base, non-protonated, plus water. Again, we're doing hydrolysis here because we're trying to isolate the base behavior. Okay, forms protonated base conjugate acid. And we say a hydronium ion, assuming it's, we're comparing it to water alone. So then the Kb would be equal to the ions produce OH minus multiplied by one another, all over the original base concentration. Important facts for these equilibrium expressions. H2O, remember, is not included because it's a liquid. Right? Notice we don't have water at all involved in the reactant portion of the expression, the denominator. Okay. I've kind of sneak peeked at this early on when we were talking about acid base strength, but a large Ka means you're a better acid, right? Because you have more ions, right? To mathematically have a larger Ka, you'd have to have more ions. Okay. So, let's see, more ions produced. So better acid slash base, depending on if you're looking at K or Kb. For polyprotic species, each round of deprotonation lowers the Ka. So that means for H2SO4, the Ka is greater than for HSO4 minus. HSO4 is a weaker acid than H2SO4 because it's starting to get a little bit more desperate to hang on to that H, that one remaining H. Okay, so also do not forget that temperature is temperature is K dependent. Just like with any equilibrium constant. For example, don't forget water. Remember, this is always an MCQ question. Water, if you put it into higher temperatures, it acts more acidic.
It's still neutral.
It's still neutral, but it's like quantified as more acidic.
But its value on the pH and the pOH scale will be less than 7.
Mhm.
Because the whole scale shrinks down.
Yeah, listen to Charlie. And then if it's lower temperatures, we quantify it as more basic. Okay. So, recall that with equilibrium, the equilibrium always favors the reaction. Actually, did I mention this before? I think I mentioned this when I started teaching about acid base. Yes. Does the acid or ionization pressure? Oh, are you saying like, does this Ka still apply when it's mixed with the base?
Yeah.
Yes, it does, but what we're trying to do is characterize it, so we just get the acid behavior characterization. If we put it in with the base, then we have a lot of other things to consider. Okay, so something to keep note about when we're looking at weak acid, weak base equilibrium is that the equilibrium, so the reversible reaction, always favors the reaction direction of the stronger acid or base. Reacting. Ooh, that doesn't look like the word reacting. Reacting to make weaker conjugate forms.
How do we know which acid or base is the weaker one? Do we just need to like memorize them?
Kind of. Or you could look at the Ka in each direction. You could look at the K values for each direction, and you have a really low Ka, or sorry, well, K in general for the reaction process in one direction compared to the other. The higher the K value,
More favored it is?
the more favored, right? The more that reaction proceeds. So this is again the table. I would honestly just let the problems teach you. Like, pay attention to what molecules they choose for what problems. And that's a really good indicator about how to know what's an acid strong, what's a base that's strong or weak on the other hand, on the flip side. Okay. I wouldn't really waste your time doing a bunch of like flashcards on this. It just isn't worth it. Get into the workbook, get into, if you haven't already, Princeton Review, right? That's a really good one. That helps a lot. And I think it's only like 20 bucks on Amazon, and it gives you like 7 like full AP like tests in there. And now it's according to Princeton Review, but it's supposed to be aligned with the AP College Board. The one thing that you want to be careful about is the AP College Board updated their like curriculum in 2020. So you want to make sure that if you get an AP study book, that it's updated in alignment with the 2020 college manual, not anything before, because before we talked about OChem and a lot of other stuff that you haven't learned. Yeah. So great. Okay. So let's do a couple sample problems of how we can predict favorability based on Bronsted-Lowry equilibrium. Actually, you don't even need me to help you with this. Just try this looking at the table. Go ahead and look at these problems and let me know what you guys think at the end. And how do I pause this? Yeah. Ooh. Would someone like to share what they chose and why? Well, we can start by writing the reaction happening between the acid, HCN, and the base, HCO3. Actually, they're both technically acids. So the question is which one's better? So it's HCN reacts with HCO3 minus in an equilibrium, because we are talking about weak, okay, to CN minus and H2CO3. And the question is, which side has the partnership of a stronger acid with a stronger base behavior? So what did we say? Let's see. Here's HCN, hydrocyanic, and HCO3, yada, yada. Here we go, hydrogen carbonate ion. So which one seems to be a better acid? HCN. So the reaction direction that we're gonna favor then is what? Are we sure about that? Okay, so HCN is a really good stronger acid, but what about the base? Well, one of these has to be a base. HCO3, and it's a really good base. But if you flip it,
Well, we have H2CO3, which is carbonic acid.
mhm,
Wait, I don't understand. Are we comparing the products and the reactants?
yeah, but we're asking which direction this equilibrium will be favored based on comparing the product and reactants as acidity and basicity behavior.
Yeah, but right now we only have the products.
Well, we do have the reactants because the products are a version of. Oh, whoa, 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 whoa,
So,
whoa,
yeah,
whoa.
you have hydrogen carbonate. We need
Hold on, hold on,
carbonic acid, it's above hydrogen.
hold on, hold on, hold on. Feel like I'm missing. There it is. This one right here. Is this one? So that is technically a better acid. HCO3 minus. HCO3 minus is a better acid. H2CO3. H2CO3 is a better acid. There we go. This is the better acid. It has the highest Ka. There we go. Sorry, guys. H2CO3 is the better acid. It has the highest K out of all of these. Okay. It has to the -7. Everybody else has to the -10, to the -11. So we would say that because H2CO3 has a really high Ka, the reaction direction favored is the reverse because this is the best acid out of all of the acids available to us. Okay.
But wouldn't it be? Because you said it always favors the one with the better acid, right? The
Yep.
one- So wouldn't that be in the opposite direction?
No, because it favors the better acid acting as an acid,
Oh,
not production of the acid. Mhm. So the next one. Da-da-da-da, is HSO4 minus and HC2O4 minus. Okay, in equilibrium with their conjugates SO4 2 minus and H2C2O4. And what we would see is that according to the table, which one has the highest Ka? Which species? Excellent. This has the highest Ka, so this is the best acid out of all of the acid options. So again, we're going to see the reverse direction favored. The equilibrium is going to find a position where the reverse is more completed or has better completion rate. Yes.
Is the KD value of the base pertinent at all in these columns?
From this acid, you could look at both perspectives, but it would just cause you to flip back and forth to come to the same result.
But isn't the base, like, don't the base and the acid have their own independent Ka, KD values? And then you have to,
Yes, but here we're looking at a series of acids and we're trying to figure out which acid is going to be the better acid out of the combo and which one's going to act like the more of a base. So we're looking, for example, these are polyprotic acids. They can act as both base or acid. You have HCO3 minus, which is a polyprotic conjugate, and HSO4 minus. So you have a species involved here that is both acid and base, which is why we're just looking at Ka here.
but I guess my question pertains to, in this case, HCO2
Mm.
or the other base, the original base in the equation.
Mm.
If that is like a really, really bad base, does that matter at all? Or?
It will still act like a base if it has to, right? That's the role that it fills, right? Because the idea is that you're not going to pull some compound out of nowhere. You're mixing these two things. So one of them is going to fulfill one of the roles.
Oh, and then on the other end.
Yeah. Yes, Annalise?
Will the acid with more hydrogens maybe better?
Generally, yes, because we know that a polyprotic tends to be stronger. Yeah. So that's actually a really easy way to see that. So this is kind of a summary table. It's kind of faint, but the idea is that you should know how to relate acid and bases. Another equation that might be helpful is Kw is also equal to Ka times Kb. So it can equal the acid concentration times the base concentration, or it can equal Ka times Kb. Okay. Also, something you should know is that Ka is equal to 10 raised to the negative pKa. And pKa is negative log of Ka. Kb is equal to 10 raised to the negative pKb. And pKb is equal to the negative log of Kb.
Same relationship between
Yep.
pH and concentration.
Yep. So the idea here is that given a variety of word problems, you might be asked to derive from information that it's not the raw form that you need, but it can get you to the raw form. You just have to see how you can get there. Kind of like cooking backwards. It's like a chef shows you a meal and you're like, hey, I know what you did in there. Or like, not because any of you guys drink wine, but exquisite wine tasters, right? They can taste like chestnut. And like, there's always like chrysanthemum or something in there. You know, like, how did you even get that in there? But it's kind of the same idea. You got to be able to see it. So let's talk about Ka problems now. We've got 3 types, okay? They're going to kind of be on repeat with Kb. And they should, by the way, they do mimic your K problems that we talked about, your unit 7, 3 types of problems, just now in the context of only acids. So, big thing to keep in mind is that since we see partial ionization with weak acids, we assume a reversible reaction and thus a process in equilibrium. That should be a given at this point. Okay, so calculating H3O plus from given Ka and initial HA. One, you got to remember that the initial acid is the prepared solution. Okay, like you're going to be told it. And then we're going to use an ice table to find the equilibrium concentrations. And then if we're given a polyprotic, we want to make sure that we calculate based off of the first. Okay, so the first ionization or the first deprotonation will characterize our math.
Prepared solution.
Yeah, it's a prepared solution. That means we know what it is. The first ionization will characterize our math. So we are going to use, if we have a polyprotic, we're going to use the Ka that goes with the first ionization, H2, not H amphiprotic conjugate. Yeah.
This is in regards to the above equation with Kw equals Ka times Kb. If Kw is a representation of the equilibrium constant, why exactly do you use Kb instead of the Ka of the other side of the conjugate?
So are you saying, why don't you use?
As in, if you have an acid and base that form a different acid and base, why can't you just use both Kas instead of using the Kb?
So this would be the K and the Kb for the same acid, and instead you're just reversing how you look at it. So this would be the Ka and Kb for a conjugate pair. So it's not the K and Kb for different chemical species, it's a K and Kb for which direction that you're looking at the pair.
Also, we're quantifying the idea that the conjugate of a strong acid is a weak base and vice versa because you multiply their Kas and Kbs together to get the 10 to the negative 14. So they're like inversely proportional how strong one is to the other.
Yeah, like a strong acid would never be a strong base in its conjugate form. That'd be kind of cool though, but it can't. So, And then we have this special math rule, which I think I kind of started introducing you guys a little bit early on with the equilibrium problems, where there's sometimes we can assume certain values negligible, right? Certain change negligible. We kind of got introduced to that concept in the common ion effect when we were like, hey, the ion produced by the solvent is going to way outcompete the ion contributed by the actual weak dissociation. So what we did was we just basically X-nayed that. Well, we have a specific case where we call 5% ionization rule in chemistry. When the percent ionization for a weak acid is less than 5%, what we say then is that another way of looking at it is when the initial concentration of your acid is at least 1,000 times, 1,000 times larger than your Ka value, which is telling you that it's 1,000 times greater than the ions that's actually going to be released, right? Because Ka is a measure of ion releasement. Okay, when it's 1,000 times greater, we can assume the impact or amount of ionization to be negligible. So we can assume specifically the change in H3O plus to be negligible. That's another way of looking. That's kind of two ways to see it. One's written in the context of ice table. One's just written generically as an overall concept. So here is the first type of problem. All right. Here we have type of problem number 1. Oh, we're doing this. Oh, this was all for type problem number 1. Gee willikers. So we're going to calculate the acid concentration at equilibrium from the given Ka and initial Ha. You will always be given Ka if you need it. Like they will not make you find it without giving you ample amount. Maybe they'll give you Kb and Kw, and then you have to use Kw equals Kb times Ka to find a Ka, but they will always somehow provide Ka if you need it, okay? So for this first problem, and notice again, I write out the steps for you so you can see a flow chart. The numbers really should just follow the process. If you understand the process, that's the most important because you're going to put this process on repeat with Kb just from the base perspective. So here we have hydrogen sulfide is a poisonous flammable gas whose rotten egg smell is perceptible. Anything with sulfur usually just stinks like real bad. Okay, that's why your toots stink, by the way. You produce sulfur gas when you fart. Yeah, that's sulfur gas being released into the atmosphere with a bunch of heat, by the way, too. You watch the thermal camera, a lot of little poof of heat. Okay, you guys are living, breathing dragons just from the other end. It's as low as 0.00047 ppm. It's also a weak acid when dissolved in water. Calculate the pH of 0.0500 molar H2S. Okay, so first things first is you want to note that Ka would be given to you. Ka is in a table. The Ka for this is 9.1 times 10 to the 8th. And we're told our initial acid amount is 0.05 molar.
Where'd you get the Ka from?
You would have gotten it from a table according to the workbook, but here I'm just giving it to you and they would have given it to you also. So what we see here is we set up our equation. So H2S reacts with water because we're not told it's reacting with anything else. We're just kind of told it's in water, right? So this is a hydrolysis reaction, a water-based, acid-based reaction where water is one of the chemical species. And it proceeds to make HS minus and H3O plus. So we set up our ice table. Boom. Yo, it didn't do that. It didn't do it right. I didn't do it right. Yo. Shazam. Bada bing. And of course, we don't care about the liquid because that doesn't help us. So what we say is we have 0.05 initially, and that's all we know. So then what we do is, of course, we have nothing in the beginning because theoretically it hasn't reacted until it mixes. Once it starts mixing, we know stoichiometrically speaking, I'm going to lose a certain amount of original acid, and I'm going to gain a certain amount of product 1, HS minus conjugate base, and pure hydronium ion, okay, with a 1-to-1 stoichiometric change ratio. So that means that my equilibrium values are 0.05 minus x, x, and x. So according to my Ka expression, 9.1 times 10 to the negative 8th is going to equal my Hs minus times my H plus all over my H2S concentration, which is going to equal x squared all over 0.05 minus x. But hold up, something to note is that Ka is at least 1,000 times smaller than my concentration. 10 to the negative 8th to 0.05, bro, that's barely gonna offer any acid ion for you. So what we're gonna say is this is negligible. So we're just gonna get rid of that x, get rid of that x. And what we get is this now simplified estimate for Ka. And from there, we then calculate that Ka, using that value of Ka, that we multiply it by 0.05 and then square root it, x becomes a value of approximately 6.74 times 10 to the negative 5th molarity, which is going to be equal to my concentration of acid. Okay. So then what's the pH? Well, then the pH is my solution is based off of negative log of the concentration of my acid at equilibrium, because that's what's going to define the pH of the solution now mixed with water. And I get that it is equal to 4.17, which is an acidic range for pH. So again, everything's lining up. Okay, go ahead and try the next problem on your own. So back to math. So what we do is ice table. Sorry, parents, it has something to do with methanoic acid, but we make it short for the fun for the kids. Not like I'm encouraging it. So
The parents are actually watching.
you know what? Some of the parents have commented. They're like, yeah, I listen to your videos. You're kind of funny. You talk really fast. And I'm like, yeah.
They do. They probably they have too much time on their hands.
Yeah. My parents have not looked at my Canvas get grades once.
Okay, so for this one, you have method 0.50 initial, 0 for plain meth and H3O plus. Negative x plus x change stoichiometrically 1-to-1 because it's a monoprotic methanoic acid or meth acid. And then you get 0.5 minus x, x, and x. Okay, so then what you do is you do the same thing here. You're going to see that the Ka is 1,000 times at least less than the 0.5 initial. So what you get then is Ka is equal to x squared all over 0.5. And you would plug in your Ka from up here, and you would get then that x is equal to some value. What was that value? Here we all got distracted by my lab partner story. I had a lot of lab partners and 9.4. 9.4 times. Okay. And you should have then gotten a pH with that value equal to 2.02, approximately. I'll tell you guys about my other lab partners in the future. They were really funny.
Are they better than the other?
Well, yeah, one of them developed a huge crush on me. And my bio teacher actually had to tell me to stop talking to him because she was like, you're really mean. You're making him, you're being unfair. And I was like, oh. Yeah. What is that? Kyle Yao taught me two L's make a W.
I've never heard that.
Yeah.
Yep, that's true.
Yeah. That's what I learned from my student. So problem type 2. Should be familiar with your equilibrium problem types. Now you're given initial HA and sorry, you're trying to find HA given Ka and pH. And by the way, pH will be the pH based off of the equilibrium amount of acid. So things to consider here, okay, is one, the unknown X goes into the initial. box of the ice table. And then never can we can never use percent ionization assumption because you don't know if that initial amount is 1,000 times more. You got to figure that out. Okay. So should sound familiar to problems that we've done previously. So here we have a problem and we're told the pH at equilibrium. We're told the pH of the solution after mixture. So what we want to do is we're going to use that pH of 3.30 to figure out the concentration of the acid at equilibrium by doing 10 to the negative pH. And that gives us a value of 5.01 times 10 to the negative 4 molarity. Okay, that's the equilibrium concentration, okay, of the acid. So then we're going to do H-benzoic or H-ben, okay, and we're going to write out the hydrolysis equation, and then we're going to see that ben is deprotonated, and H3O plus is created. So we set up our ice table. And of course, the water does not matter. And we say to ourselves, well, I don't know what this is. The initial benzoic acid is protonated. And I don't really know. Okay, this is obviously 0 and 0. Okay, I don't really know much else than that, but I do know the equilibrium of the acid. So the equilibrium of the acid is 5.01 times 10 to the negative 4th. And that means, by the way, I have added 5.01 times 10 to the negative 4th. Well, stoichiometrically speaking, that means I have also had an added amount of 5.01 times 10 to the 4th for my benzoic deprotonated form. Okay. And that also means that I have subtracted 5.01 times 10 to the negative 4th from my original initial acid amount that I'm trying to figure out. Because stoichiometrically speaking, it's a 1-to-1-to-1 ratio change. Okay. So then I get that my concentration of my equilibrium value for benzoic acid deprotonated is 5.01 times 10 to the negative 4th. And my equilibrium value of my initial is x minus 5.01 times 10 to the negative 4th. And so what I do then is I simply say, well, I'm going to plug this in now into my Ka value. So my Ka here, you would look it up or be given it in a table, is 6.5 times 10 to the negative 5th, okay, which is equal to, I just plug it in, my two products multiplied by one another, so 5.01 times 10 to the negative 4th squared, because it's multiplied by itself, all over x minus 5.01 times 10 to the negative 4th, because that would be my reactant on the bottom concentration. And I would solve then for x, and x is equal to, okay, 4.4 times 10 to the negative 3 molarity. So totally same process that we've done in the past with the 3 types of problems you can have with general K equilibrium problems. Now this is just specific to an acid. That's all. You're doing it all over again. And you're going to do it a third time when I talk about bases tomorrow. Okay, we're going to save this for a warm-up problem tomorrow. And let's move on to type problem 3. So the final problem, this is your favorite one. This is, by the way, this is your plug and chug one. This is the one that you want to get, okay? Because what you're doing is you're going to calculate Ka given your HA and pH. And your pH, again, is going to reveal the equilibrium concentration of that acid. It's the pH of the solution once mixed. So you're so focused right now. So for this one here, we're given that we have a pH of 2.27. So I'm going to figure out what the H3O plus at equilibrium is. And that's going to equal 10 to the negative pH, which is going to give us a value of 5.37 times 10 to the negative 3 molarity. Okay. And then I'm gonna set up my ice table. So I'm gonna have H acetylsilic acid. Sorry, I see how I shortened that. That was unfortunate. So H as acetylsilic acid reacts with H2O hydrolysis, right? We're just isolating the acidic behavior. Forms conjugate as minus and H3O plus. And what you do is you just do your table. You fill in what you know. Well, I know that water doesn't matter. Okay. I start off with 0.
Just zoom in a bit.
And I had an original amount, according to my problem, of 0.100 molar of my acetylsalicylic acid. Okay. And then I know that my concentration at equilibrium is 5.37 times 10 to the negative 3. Well, then I say, well, that means I have changed then. I have changed by positive 5.37, positive 5.37 for my 2 ions produced, and subtracted negative by 5.37 for my reactant used up. And then I get a value when I do my equilibrium values. Ooh, gee willikers. When I do my equilibrium values, I get 5.37 times 10 to the negative third for my 2 ions and 0.100 minus 5.37 times 10 to the negative third to give me a value of, I don't know what that is. Anyone want to do that math? Okay. Well, 0.1 minus 5.37 times 10 to the negative third. That'll give me some value. Yo. Yo.
It's 0.0463.
0.0463. Thank you, Malcolm. 0.0463. Excellent. And then all I do is I got to find what Ka is. I plug this all in and I just do the math. Ka is equal to 5.37, my ion products multiplied together, together, times itself, so squared, times 2 of them, right? All over my original equilibrium acid, so 0.0463, and I should get a value of where am I? 3.0 times 10 to the negative 4th for my Ka. Then okay. That should be what it is if all the math ends up being correct.
And does Ka have units?
No, K does never have units, never have units. So that's that. And then we'll warm up with this problem tomorrow, and then we'll do the same thing with the base perspective. Good job, you guys.